Let's see how we can use CNN-based face recognition to identify or detect faces in an image. We need input, which is an image containing a face, often cropped to standard size, like 160 by 160 pixels. CNN feature extraction, which extracts high-level features like the shape of eyes, nose, mouth, distances between facial landmarks. Embedding vector, the CNN outputs a vector, often 128 or 512 dimensions, that uniquely represents the face. Matching faces, you compare vectors using distance metrics like cosine similarity or Euclidean distance. Sometimes we use at the end classification step. If you have labeled identifiers, you can train a classifier, softmax or SVM, on top of the embeddings to recognize specific people. Let's see these steps in code. The pipeline, the image, then the face detection, which we will use the MTCNN library, then face crop and resize, then the CNN, where we recognize the face, and we will set the confidence threshold to accept or to remove some images that we don't want, and then known and unknown. First of all, I want to have access to Google Drive, so you will mount the drive so that you can use your folders and files from Google Colab. This is the dependencies that we wanted in this code example. We will install MTCNN, TensorFlow, OpenCV, Python, and Matplotlib. Please, you need to recognize your dataset in this structure. So you will save the train examples inside folder called with each people. For example, I want to identify Zilal, which is me, Ali, Muhammad, and then folder known or named unknown. And then a folder called val to install the images for validation step. This is very important. So the classes that I want to use here for Zilal, Ali, Muhammad, and unknown. This is the code where we use the model sequential. We will use 32 filters, which is the feature maps with kernel size 3 by 3. Each filter is a 3 by 3 kernel that detects specific patterns in the input image, like edges, corners, and so on. So the first layer produces 32 different feature maps for each image. Activation function ReLU to introduce nonlinearity. And of course, here we are using colored image, so we will have the 3-channel RGB to set the image here channel to be 3. After the convolution layer, we will use the max pooling 2D layer to reduce spatial dimensions by half. This helps CNN focus on dominant patterns, and we set it to be 2 by 2 dimension. Then I will use another convolution layer, which has the 64 filters. More filters detect more complex features like faces, eyes, nose, mouth, textures, and so on. After the convolution layer, we will use pooling layer with 2 by 2 dimension. I will use a third convolution layer with dimension with the, we call this, as I mentioned, this is the feature maps. So the number of filters will be 128 with activation function ReLU as well. Then followed by pooling layer. Finally, we will use flatten, which converts 3D feature maps to one vector, which prepares data for fully connected layers. The dense, this one, dense layer. Fully connected layer with 128 neurons learns high-level representations. For example, combination of eyes plus nose plus mouth, will give me the identity of the person. Then we will use dropout with half. This randomly sets 50% of neurons to zero during training. We don't use this in the testing or validation, just in training step. This to prevent overfitting. It means the model will generalize better. Finally, the dense layer with the number of classes and activation function softmax. Next step, which is the data augmentation and generators. I will use image data generator from TensorFlow keras.preprocessing.image, which enables us to generate images on the fly. For example, here you can use rotation range equals to 20, which randomly rotates images by positive or minus degree 20 degrees. Width shift range equals to 0.1 means shifting the image left or right by 10% of width, which teaches translation invariance. Height shift range equals to 0.1 means shifting image up or down by 10% of the height, and so on. So this will enable us to generate images on the fly. It will not store the images. It just will use it in the training the model. For the validation data, this will represent the real untouched data. So this line creates an image data generator for the validation dataset that only normalizes images without applying any data augmentation. Why we do this? Neural networks train and evaluate better with normalized input. So the output will range from 0 and 1. Here, the train generator. So here we will train generation that we will receive from this image data generator. We will put it in flow from directory to point to our training dataset folder and expects a subfolder per class, as I mentioned, each person's face in face recognition. The target size to ensure the input matches the CNN expected input size, and the class mode to be categorical. The output labels are one-hot encoded. And for the val gen, the same. So the output will tell you how images you have with how many classes you have. Now the training process. We will use the fit method from the model, and the parameter will be the train generator, validation data, and the epochs. The more epochs you have, the more accurate result you will end up. Now let's use the face detection and recognition. By this library, MTCNN, it is a deep learning based face detector, not a face recognizer. And then CV2 and NumPy and Matplot as PLT. So this is a initialization of the MTCNN, and the threshold, it will be, you can play with this as you want. Of course, if you set it for example, 90%, then any faces that not very similar to the face that we want will be ignored. And this is the number of classes we are using. In my example, I'm using 4 classes. Now let's see how we can use MTCNN, which is a deep learning based face detector, to detect faces in an image. This is not a face recognizer, with the help of OpenCV and NumPy. This is the threshold that you can play with it. The higher the threshold, the more images could be ignored. And this is the classes that you are using in your code. This is the code where you define the function that takes the path to the image. And this is OpenCV loss images in BGR format, blue, green, red. So we will use the method color BGR to RGB to use it with matplotlib because it expects RGB format. And here we are looping over the faces in the images. And this is to match the CNN input. We are dividing by 255 to normalize pixel values between 0 and 1. So to match pre-processing used during training. This is the MP expand dimension. We are adding the batch dimension. CNN expects batch of images, even if it is just one. So the shape before, it will be image size by the number of channels. After this step, the dimension will be 1 for the batch size, and then image size, and the number of channel. So if you test it with tree image, for example, if you saved trees in unknown folder, and I tested with Layan picture in the validation folder, you will notice the output for the tree to be no face detected because it's a tree, not a face. And for Layan, you will detect the Layan face. This is the name of the class, and this is the confidence. Now I will show you another way to recognize faces in an image which is more accurate without using CNN being training by us, which is the face recognition library. You need to install it with the OpenCV-Python. Then you need to organize your images. Folder name equals person name. Inside each folder, you will have the images of that person. For example, in my case, the folder named is Zilal with my images. Then we will encode the faces. We generate face embeddings for each person. These are 128 dimensional vectors representing the face. Remember that the model or the machine understands numbers. It doesn't understand faces or images. This is the numbers that we use it to represent the face. And here we are importing the face recognition and the OpenCV to recognize the face. You have to specify the path for your training examples. Remember to point to the train, which will contain the folders of each person. And here we are storing the embeddings and the names. Then looping over the images to install and append the encodings and the known names. And here we are testing by using an image which contains people, and it will just recognize Zilal because I didn't train it to identify the other persons. And here find faces and encodings in the test image by using the face locations and the face encodings, passing the test image and the test image with the face locations. And here we are converting to convert to OpenCV format for drawing. Remember that OpenCV expects RGB, inspect GPR instead of RGB, and that's why we are using the color underscore RGB to BGR. And this is the locations of the top, right, bottom, left for each face. And if the face is not recognized, we will label it as unknown. Then to draw the box around the face. Let's summarize what we have done in this face recognition example. Face recognition encodes each face into a 128-dimensional vector that uniquely represents the face. Face recognition uses dlib plus a ResNet-based CNN internally to generate embeddings. So technically it is CNN-based. When you use face recognition dot face encodings, you're already getting CNN embeddings. The difference, face recognition abstracts away training. It's ready to use. We didn't train a CNN. We didn't use CN convolution layer, pooling layer, or dense layer. We just used the face recognition library.